Earlier this year, I posted a poll on YouTube and the Patreon Discord asking what you were interested in seeing in 2023 from this channel. Most of you said rocket motor development for the BPS space shot, and for the last 4 months I've been doing just that. So let's begin. Fire. This is the first in a series of videos I'm making about Simplex, an O-class rocket motor that I designed, built, and then fired over the last few months. The current plan for the BPS space shot is to do it as a vehicle that is 2 stages. Each stage has a rocket motor that is about 7 to 8 feet long, 6 inches in diameter. It has about 100,000 newton-seconds of total impulse, which puts it in the Q class of rocket motor range. So they're big motors. These plans are definitely going to change as the design moves forward, but the one thing that will not change is the diameter of the rocket, which is 6 inches. The reason we're sticking with this is that I am constrained by my machines in terms of how big I can build these rockets. So my Tormach mill, my eBay lathe, and even down to my 3D printer all set the constraints for the amount of width that these rockets can have. As it stands, I can make about 90% of the parts that we need for this space shot on these machines, and if we were to go from a 6-inch diameter up to a 7 or 8-inch diameter, that 90% number is going to go a lot lower. Now, I have never built my own solid rocket motor, but I do know a lot of people who have, so with their help, guidance, and support, I decided to start out by building a 6-inch diameter rocket motor. For what it's worth, this is not an approach that I recommend, but I did choose to go this route, so that's what you're seeing here. The reason I did this, though, is that all of these parts for the rocket motor back here could, in theory, be put on the larger Q-class rocket motors that we need for the space shot, which means that right at the start, we're already designing for the scale that I want this thing to be. This means the big difference between Simplex and the eventual space shot motor is almost entirely just length. There's a little bit of propellant geometry too, but we can basically make the motor longer or shorter depending on what we need. Okay, one more thing before we get started. These videos are not a tutorial. They might look like it, but I promise you they are not. My goal is to make these as a resource, and you can certainly learn from them, but if you are building your own solid rocket motors, you need to be working with someone else in person who has done it before a bunch of times. Safety is usually very important with the rockets that I build, but I want to be really clear. The level of safety here is a lot different. This is a different flavor of safety. The chemicals that you need to work with in order to make a solid motor can kill you either quickly in a fire or slowly through cancer. The machines that you work with in order to make the hardware can kill you, either quickly or it's mostly quickly with the machines. And obviously this thing is a rocket motor, so there is one time and one place in which it is okay for this thing to be burning, and a billion that it is not. This means you have to think very hard about how to make sure the motor never burns when it's not supposed to, and even when it burns, things can go wrong. Your propellant can be fractured, you can have a case burn through, you can have a motor overpressure. So many things can make your motor just explode, and that is, for obvious reasons, not great. And usually this is the part where I would tell you that I'm not trying to scare you, but I actually am. You should be scared. These are scary things, and it is good to be scared of them. If you're building your own rocket motor and you're not just a little bit on edge or aware of the risk, you are probably too comfortable, and comfort gets you hurt. All right, that's my disclaimer. I just want to make that very clear. This is like normal rocketry safety, and this is motor building rocketry safety. But with that in mind, now let's talk about the different parts of a solid rocket motor. Okay, so we've got a cross-section of a solid rocket motor here, and we're going to start from the inside out with the rocket propellant. That's this gray thing here with the core in the middle. The next thing we're going to add is a nozzle. It has a converging, straight, and diverging section, and we call that straight part the throat. So we've dealt with the aft of the motor, but on the forward side we also need to thermally insulate so that the fire doesn't come out the top, and we'll do that with what's called a forward insulator. This is going to keep things cool on the front end of the motor. I'll add some extremely realistic fire here, and then we need to deal with the thermal situation on the side of the motor. We're going to do that with this brown line called a liner. The liner acts as an insulator between the rocket propellant and the eventual case that we're about to add. And here's the case that I'm adding in white. The case is the part of the motor that holds all of the radial pressure. There's a ton of force inside that rocket motor, and the case keeps everything put together. But because the case is a tube, it can't hold the pressure at the end, and that's why we have what's called a forward closure in green here. And finally, if we didn't have anything at the bottom, the nozzle would just fall right out. There's more pressure on the inside of the rocket motor than there is on the outside, so we retain that rocket motor nozzle with what's called a retaining ring, or sometimes called a nozzle carrier. And that's it. Now you are a total expert who knows everything. So we know the parts that we need to make for this rocket motor, but we also need to know how it is going to burn. And obviously, like, fire burns, hot gas does hot gas things, but I'm talking about designing the geometry of each propellant grain. By the way, a grain of propellant is just a section of propellant. For instance, this is a propellant grain. Propellant comes in grains because it makes it much easier for it to ship across the country and move around, and it happens on the scale of hobby motors like this all the way up to the space shuttle rocket motor. That thing got shipped around the country in different sections using train cars. Also, this is a moon burner grain, which is really cool. It means the core is offset from the center, and we're going to talk about propellant geometries in just a second. To simulate how this rocket motor is going to burn, I'm going to be using a program called OpenMotor, which is what's called an internal ballistics simulator. The program can take in data about the characteristics of the rocket propellant you're using. You can define the shape of your rocket motor and the internal geometry, and then it will simulate how that rocket motor will burn. You can use the program to get an estimate of your thrust force, chamber pressure, and Kn, which is an arbitrary value relating the surface area of the burning propellant to the throat of the nozzle. OpenMotor will also show you the cross-section regression of the motor grains, so you can see how the geometry within the motor will change as the burn occurs. All of these things will change as a function of how the motor is currently burning. It's like a bunch of differential equations, which makes a program like this really powerful. So the design for this motor includes two sections of geometry. Each one has its own shape. One is a straight cylinder, and the other is something called a finicyl. See these little fin sections? See how they're around a cylinder? Fin-o-cyl. Pretty cool, huh? Different shapes of the propellant cross-section will cause the thrust curve to take on different shapes. And this finicyl and cylinder setup is actually pretty common. For the cylinder section of the rocket motor, I selected a core of 2.5 inches because I knew I could buy a piece of stock material to make the mandrel so that we could cast the propellant into that section. And then the finicyl shape and height was selected so that I would be able to 3D print that section as a mold. With Simplex, we're going to place the finicyl section at the aft, which means we're going to put it closer to the nozzle. And the reason we do this is to minimize a really annoying phenomenon called erosive burning. Basically, when the hot gas at the top of the rocket motor moves toward the nozzle, it picks up a whole lot of speed, and that speed actually changes the burning characteristics on the surface of the propellant lower in the motor. By putting the finicyl down at the bottom, we can open that section up sooner and get rid of the erosive burning sooner. And the reason I tell you all of this is because OpenMotor actually cannot simulate erosive burning. It's quite hard to do. Or at least I should say, it's not something that the program can do yet. OpenMotor is a program developed by a brilliant engineer named Andrew Riley, and he made it open source. So if you're interested in helping with the development or checking out some of the source code, you can go visit the link in the description down below to check it out yourself. Otherwise though, we end up with this as our final thrust curve, this as our pressure estimation, and lots of other information down here. Our thrust curve hovers between 4,000 and 5,000 newtons, and the impulse is right in the middle of the O classification with an ISP, or specific impulse, of around 194. This is like okay for a solid motor, but our goal isn't performance here, our goal is to learn. The pressure peaks at around 720 psi, and we have just shy of 40 pounds of propellant. Speaking of propellant, by the way, when you think of a solid motor, you generally think of APCP, which stands for ammonium perchlorate composite propellant. APCP is an idea of a propellant. It's not an exact formula or mixture. The formulas are going to dictate a lot about how your rocket motor burns, and that depends on a whole lot of things. We're going to talk a little bit more about propellant formulas and how they work in the next video, but for this video, what you need to know is that we're using a formula called cherry limeade. It was developed by the MIT rocket team a few years ago, and most importantly, it is available online to learn about. We're also using this propellant because after I flew Lumineer almost 2 years ago now, Charlie Garcia and I had tentative plans to build Lumineer 2. The idea is that we would use about 40 pounds of cherry limeade to build a big motor for another Lumineer and send it up even higher. We never got around to making that that rocket motor, but we had already purchased all of the 40 pounds of propellant chemicals to make it, so we figured we'll just take those and make Simplex with them. Finally, here in Open Motor, I selected the throat shape and size by dialing in where I wanted the pressure of the motor to sit. 800 psi is a nice range for hobby rocket motors to sit in, and shooting just a little bit below that gives us some margin in case something goes wrong during the casting process. Now, I'm sure nothing will go wrong in the casting process, right? There's no reason to believe that something would go wrong during the casting process, and I don't know why I'm even suggesting that something would go wrong in the casting process, because I'm sure it will go fine. But it's nice to have that little bit of margin there. Okay, now that we know what our thrust curve is, we know the propellant geometry and the nozzle shape, it's time to take these ideas and turn them into designs through CAD. We're gonna do this using the sponsor of today's video, which is Onshape. If you've followed this channel for a little while, you know that Onshape and we go way back. If you don't know though, Onshape is a modern CAD platform designed for businesses and is free for hobby and maker uses. I have used Onshape personally for a lot of my older projects, like the model Falcon Heavy. I've tried a few other programs in terms of CAD, but as of this year, I'm switching back to Onshape for its flexibility and ease of use. It's a cloud-based CAD software, which means you can take your designs pretty much anywhere you go on most devices. It also makes file management so much easier because of the GitHub-inspired approach that it takes. When big changes occur, you don't have to create like 17 different versions, V1 through 17. You can just branch off of the design like you would with a piece of code in GitHub. Onshape was also created by the founders of SolidWorks, which means that you get all of the good parts of legacy CAD softwares while ditching some of the clunkier ones. Whether you're a business or a hobbyist, you can try out the free Onshape plan by going to onshape.pro/BPS.space or visiting the link in the description down below. Thanks again to Onshape for sponsoring this video, and now let's design this motor using it. All right, so let's design this thing in CAD, and we're gonna start from the outside in. On the outside, we need a case, and so we're going to go with an aluminum T6 6061 1/8 inch wall case. This is just gonna be a piece of stock material that we order as a tube from a stock material website. The bursting pressure when this tube is sealed is going to be roughly around 1400 psi, which is a thing that we should talk about. After doing a whole lot of math, I have finally determined that 1400 psi is greater than the 800 psi chamber pressure of the motor, but it is not that simple. I selected the 1/8 inch wall because the mass savings on the Space Shot rocket were just bonkers. It turns out that if you go from a 1/4 inch wall rocket to an 1/8 inch wall rocket with the design that we have, that is the difference between going to like 105 kilometers and 170. The thing is though, your design pressure is not always the pressure that your motor operates at. Actually, often with hobby motors, this is the case. What if there's a crack in your propellant? What if your mixing process is a little bad and your propellant burns faster than you expect? What if your thermal insulator isn't good? You have a little hot gas hit the case wall, and now that case that would usually burst at 1400 psi at room temperature has its bursting pressure greatly lowered. The yield strength of a hot metal is usually going to be lower than the yield strength of a cold metal or room temperature metal. I'm not sure how familiar you are with solid rocket motors, but one thing I can definitely tell you is that they get hot. The case is still here, the motor fired fine, but I'm just here to tell you that designing with an 1/8 inch wall for something like this is a little bit spicy. The next thing we need in our design is a nozzle, and we're going to do this in a few parts, so let's start from the outside in. The outside of the nozzle assembly is going to be a big chunk of aluminum for this design, and it's going to carry the nozzle, so we'll call it a nozzle carrier. On the outside of this piece, we're going to place 2 O-rings, which are going to seal the pressure inside the motor case. If we didn't have these, all of the hot gas and pressure within the motor would escape between the nozzle carrier and the case. Also, a quick word on O-rings. These things come in lots of different shapes of sizes. You've got big O-rings, small O-rings, O-rings that climb on rocks. This is the one we're going to use to seal between the nozzle carrier and the case. And here's the thing with what I'm doing. This case is just stock material that comes from the mill. Obviously, it's a lot shinier now. But because of that, there are small imperfections all over the place with this. You've got little nicks and bumps, and especially for this, the case sometimes has dents on the side, it's slightly out of round, it's not totally circular, so it's not a perfect sealing surface. One way to deal with that type of uncertainty is to choose very thick O-rings, because if you think about the cross-section of an O-ring, a thicker cross-section is going to have more sealing surface area around it. I used the Parker O-ring handbook to set the dimensions for these O-ring grooves, and I selected the largest rings that I could. Larger O-rings generally have more resistance to rolling around in grooves and are pretty tolerant of small imperfections. The only downside to these big O-rings is that they require a stupid amount of force to get them inside the tube, and we'll talk about that in a future video. Now we need to retain this nozzle in the case. The O-rings O-rings are going to seal against the pressure, but they're not going to hold it. And we're gonna do that using radial bolts. For this nozzle carrier, we're going to do this with 28 M5 screws. And this is a very big number of screws. I'm sure you're very curious as to why I picked that number. I'm not going to get into the math right now because we would be here for 6 more years, but let me tell you some of the things you need to calculate in order to arrive at a number like that. First, you need to know the shear strength of the material you're using, and you can either use bolts here or pins as well. Then you use that to determine the failure point of that bolt or pin. For bolts, you want to make sure you use the minor diameter in the threads to calculate that. Then you need to think about the tear out strength of the case. When the radial bolts are closer to the edge of the material, they're more prone to ripping out of the case under high load. Other important factors are bolt spacing distances, which is why there are 2 rows of bolts here. Spacing the bolts too closely together can also cause the case to fail along the bolt line. And it's also worth considering that we live in an imperfect world with imperfect machines. Some of these bolts will be taking more of the load than the others because the holes aren't all perfectly in line with each other. Getting super generous with safety factors is a great idea here, and countersinking the bolts can also help with this too. There's also a whole nother side of this discussion that is around safety and planned failure modes for this case, which we are not going to get into here. But there are some scenarios where you would rather have the nozzle fall out than the case explode, and sometimes designing like really tight tolerances or really tight safety factors on these bolts is actually better for safety than letting the case blow up. But we're not getting into that. We're not gonna go down the tangent. We're not gonna do the rabbit hole. Okay, with the nozzle carrier done, we can move on to the inner phenolic section. Phenolic is an amazing material, and it is an ablative. Phenolic is one of the main materials that's used in heat shields for most space capsules. The material chars and ablates away when hit with hot gas, which makes it a fantastic insulator, but it is a little bit nasty to work with. We're gonna use this material here in terms of phenolic, which is linen phenolic. This means that you have a bunch of sheets of linen that get put on top of each other, and then as you go, you put phenolic resin in there. It's like an epoxy resin, so it's sort of like doing a regular composites layup, but it's just way better at heat. Finally, for the throat of the rocket nozzle, we're going to use iso-molded graphite. I have a big piece of it here. This is basically like the world's largest pencil. Graphite is an incredible material, and it's also a terrible material. It's incredible because it barely erodes, and it can take a tremendous amount of heat before melting. And it's a terrible material because it will destroy your machines. Any dust that you get from machining graphite will, over time, erode and like abrade away your machine. The shapes of all these pieces fit together as a taper, and then the adhesion between the pieces is going to be done with something called RTV silicone, which is room temperature vulcanizing silicone. RTV is a high temperature gasket maker, which means that when the motor comes up to pressure, these parts are all going to squish together into each other, and it's going to create a really good seal between all of them. This design is actually pretty cool too, because it means that the force from the rocket motor will actually create a better seal. Like, higher pressure will improve the seal, which is cool. So that's all there is for the nozzle, and the only other thing we need here is a forward closure, which is what's going to prevent all of that gas from coming out the top of the rocket motor. The outside of this is going to be a mirror image of the nozzle carrier, which means it has those 2 O-ring grooves and the same bolt hole pattern. We're also going to place a phenolic insulating disc up at the top here, and another small O-ring groove that will fit a ring between the closure and the thermal insulating liner. Here's the reasoning behind that. When the motor fires, the hot gas at the forward end of the motor is moving relatively slow and the pressure is relatively high. Near the nozzle, the gas velocity is much higher, and because of Bernoulli, that actually means the pressure is lower. This gas at the top will want to find any way it can go from that high pressure to that low pressure, and sometimes that might mean that it escapes out between the liner and forward closure, then tries to go down to the nozzle in the small gaps between the liner and the case. This is a very good way to have a rapid, unscheduled disassembly of your rocket motor, so sealing the liner at the top is a great move. It's also worth noting here that we do not want to seal the liner at the nozzle. We want that to be an open gap. That's because if we seal it at the nozzle and we seal it at the top, the thing that's actually holding the pressure first before the case is the liner. Linen phenolic is a pretty brittle material, and it's not going to be able to hold all that pressure, so your liner is likely going to crack, and then you're going to have a burn through, and then you're going to have hot gas on the case wall, and then you're also going to have a rapid unscheduled disassembly. It turns out, weirdly enough, rocket motors are really easy to blow up. The last 2 things on this forward closure are these 3 holes around the center and 1 right in the center. The 3 holes around the side are for redundant pressure transducers. It'll be helpful to see what the chamber pressure in this motor actually is. And the center hole is for something that I call the HEI bolt, which stands for head end ignition bolt. This is a massive M30 bolt that's going to thread into the forward closure and has all of the ignition compound on the top here. Just so we're very clear, there's no ignition compound on this right now. This also helps us greatly in the design of the second stage for this space shot rocket. Having a head and ignition system like this can be a little bit dangerous because your igniter is integrated in the motor for longer. So we solve that by having a bolt that simply threads into the rocket motor, and then you're ready. We're going to talk a lot more about that HEI setup in a future video, but that's pretty much all I want to cover in this design video. I am so excited to finally be sharing all of this content with you, and I'm going to get these videos out as fast as I can. But if you are not that patient and you are ready to watch hours of content instantly, every 2 weeks this year, I have been making a longer and longer video recapping the last 14 days of what I've done with BPS. As we gear up for the space shot, I am trying through sponsorships and Patreon to make sure that we have the funding to support that type of project, and one of the ways that I've been doing that is that every 2 weeks I sit down with a microphone and all the footage from the last 2 weeks, and I just show you what's up. It's a great way to stay in touch with the things that are happening in real time on this project, and as I get these videos out, if you're looking for more detail or just want to see a more casual approach to seeing how I built this rocket motor, supporting this on Patreon is a good move. Thank you so much to the folks who financially support this project through Patreon and otherwise, and thank you to you for just watching. A lot of the information in these videos is not super interesting to most folks, but by sticking around, it means a lot to me. I appreciate you all following along as we go on this crazy journey to 100 kilometers. So thanks again to Onshape for sponsoring this video. My name is Joe Barnard. May your skies be blue and your winds be low.